Next, we've got prefixes. So prefixes are just another way of writing scientific notation. So whenever you see kilograms, kilo is a prefix that means 1,000, right? So a kilogram is 1,000 grams. So we are, on your formula sheet, going to have a list of prefixes and what scientific notation they fit with. And so it's really just shorthand for scientific notation. That's the way that you should think of it. So 5.0 times 10 to the negative 6 meters is how many micrometers? So micrometers, this micro part, if you look on your formula sheet, means times 10 to the negative 6. Okay, that's what the prefix micro means. And so when you see 5 times 10 to the negative 6, this 10 to the negative 6 is the same thing as micro. And so this is really just 5.0 micrometers. That's it. So a prefix just takes the place of scientific notation. It sometimes is straightforward like that. The scientific notation just matches the prefix, and they're easy to swap in and out for each other. But sometimes it's not quite that simple. So the second one here, 10 to the power of 9. Check that out on your formula sheet. What does it say? You don't have it in front of you? Well, go and get it. Okay, now we're good? So, 10 to the power of 9. It matches with giga, right? So if you look up the G, it'll say 10 to the power of 9. And so then you can just put in 6.4. So 6.4 gigaliters is 6.4 times 10 to the 9 liters. Giga means times 10 to the 9. 26 megaseconds, look that up. Look for the big M. Yep. It's 10 to the power of 6. So this is 26 times 10 to the power of 6. 26 times 10 to the power of 6 seconds. Oh, some of you have gone, wait, that's not how scientific notation works. You said that you're supposed to put the decimal after the first number. The decimal is after the second number there. You're right. So if we wanted to make this proper scientific notation, we should really say 2.6 times 10 to the power of 7, right? We're taking another 10 out of this 26 and making it 2.6, and we've got to store that 10 in the exponent. Okay, and so it becomes 2.6 times 10 to the 7 seconds. The last one here, 15 nanometers is how many meters? Look up nano. Nano is 10 to the negative 9. And so this is 15 times 10 to the negative 9 meters. But again, that's not quite right. So I'm going to write that down, 15 times 10 to the negative 9. But that's not quite right because, again, we want to put the decimal over here between the 1 and the 5. And so if we want it to be 1.5 times 10 to the something meters, what's it going to be? Is it going to get bigger or smaller? It's going to get bigger, right? Because we're taking a 10 from the 15 and we're putting it in the exponent. And by bigger, I mean that this number, this digit, is going to move to negative 8 instead of negative 9. Okay, so it's not going up, it's not going to negative 10. Up and down gets confusing when you're talking about negative exponents. But it's going to move to negative 8, which is larger than negative 9, right? So this is correct, 1.5 times 10 to the negative 8 meters. Now I mentioned that sometimes it gets a little bit more complicated than that, right? Just switching the scientific notation into a prefix. Sometimes they don't actually match each other. So if we look at this example, 22 times 10 to the 8, and yes, this is not perfect scientific notation, but let's just go with it, okay? 22 times 10 to the 8 seconds. 10 to the 8 does not actually match any scientific notation. It's close. Times 10 to the 9 is exactly giga. So this guy over here, this prefix is 10 to the positive 9. And so if we could somehow make this 10 to the positive 9, then it would match giga. So what do we need to do to the 22 to make the times 10 to the 8 match times 10 to the 9? We need to borrow one more 10. We need to take another 10 from the 22 and put it in the exponent, and that would make it 10 to the 9. And so if we make this 2.2 instead of 22, now it becomes 2.2 times 10 to the 9. Okay, so this is 2.2 times 10 to the 9 seconds. That's the same thing. And now this times 10 to the 9, that matches giga. And so now we can just take our 2.2 and exchange the 10 to the 9 for the prefix, and so now it becomes 2.2 gigaseconds. Okay, that one's hopefully okay. Sometimes the difference is a lot more than one decimal place that you need to deal with, and so it can get a little bit complicated. So please do the practice for this section, even though it's just background stuff and it's not the actual physics. Okay, so 6.44 times 10 to the negative 7 is how many nanometers? Nano is 10 to the negative 9. So this 10 to the negative 7 does not match the 10 to the negative 9. So the question is, what do we have to do to the 6.44 in order to make the 10 to the negative 7 turn into 10 to the negative 9? Think about it. I need to borrow more 10s, right? So I need to take 10s out of this exponent here. I need to take 10s out of this exponent and put them back into this number. Okay, so I want to take a 10 out of there, which would make this 10 to the power of negative 8, and put it into my 6.44 number, which would make it 64.4 times 10 to the negative 8. Sorry that all these lines are in the way now. But do you see what I'm doing there? I'm taking 10s out of the power, out of that exponent, and I'm putting them in the number at the front over here in order to make the exponent match the prefix that I'm going for. Okay, and so I need to do that one more time in order to get 10 to the negative 9, which makes it 644. Okay, that is going to take some practice. That's going to take a few times looking through it to get your head around it. So re-watch that part of the video, try the practice, do what you need to do. Last one, 44 centimeters is how many hectometers? Centa is 10 to the negative 2. Hecto is 10 to the positive 2. And so I want to add 4 10s to this guy. Right? To go from negative 2 to positive 2, I need to add 4 10s to that thing, which means I need to take 4 10s from 44. So that would be 1, 2, 3, 4 10s. So that would make it 0.0044 times 10 to the positive 2. So I have taken 4 10s out of the 44 and I have put them into the exponent. And that has changed my exponent from negative 2 to positive 2. It's gone up by 4. And that now matches the hectometers. So my answer now is 0.0044. Okay? You're not going to do this a lot. Okay, so prefixes are mostly going to be found in one specific part of the course or a couple different parts of the course. You're not going to do it every single day, not on every single problem, but this is still an important skill to get your head around. Okay, so please don't skimp on this practice. We are going to skip the graphs part in your notes book for now. We're going to talk about how to use graphs and graphing skills and all of that stuff in context when we need it. Okay, so we're going to skip the graph stuff for now and move on to angles. And this is going to be really brief. So because in physics we are often talking about vectors and not just scalars. So a vector is a quantity that has both a size and direction. So 100 kilometers per hour is a speed. 100 kilometers per hour north is a vector. It's a velocity vector. And so often we have to use angles in order to describe directions properly. And clearly, that's the point. We want to describe directions clearly so everyone knows what we're talking about. So we all need to know, how do we describe angles, or how do we write down an angle correctly so that everyone knows what direction we're actually talking about. So the way that I really like to do this, ignore those blanks up there, we're just going to go to the examples. The way that I really like to do this is number 1. Number 1 is my favorite. I think it is the clearest. Mr. Fast might disagree with me. I don't even know. We haven't had this conversation. So if he gets mad at me at this point, you know, just go with it. I'm right anyway. So this is the direction that we're looking for. This is a graphical representation of a vector. I'm looking at this guy over here. So this vector is pointing northwest. And specifically, if we look at this angle over here, we get 40 degrees in the northwest direction. But it's important to tell the reader where you started measuring that angle and which direction you rotated it toward. So we started measuring this angle to the west. Let me grab a different color really quick. So we started measuring it toward the west. That was our 0 line for the angle. And then in order to measure it, we rotated our measurement upward toward the north. So we started our measurement from the west and we rotated it upward toward the north. And so that's what this guy means over here. When you write down west 40 degrees north, you're saying I started measuring my angle at the west and I rotated it upward 40 degrees toward the north. Okay, I like that one the best, find it the clearest. It's not the only correct one. All these other ones on this list are also correct. This 40 degrees northwest, that one is technically correct. I like that one less because often people who don't actually know how to write the angle clearly just use that one because they see that the vector is in the northwest quadrant over here and they see it's 40 degrees. And so 40 degrees northwest, and that's it. But that's not necessarily correct. If your vector was like this, and this was 40 degrees, you could not say 40 degrees northwest. That would not be correct. So what 40 degrees northwest means is 40 degrees north of west. Okay, it's just omitting the of for being briefer, I guess, for brevity. And so it's easier to write, which is nice, but it's a little bit less clear. But if you know what you're talking about, you are welcome to use that one, okay? 40 degrees north of west. So we started west, we measured 40 degrees north of west, and that's where our vector landed, okay? The other two are just other versions of the same thing. So this one over here, north 50 degrees west, we started measuring from the north over here, and we measured it 50 degrees toward the west. And if you know that this whole quadrant here adds up to 90 degrees, then if this bit is 40 degrees, then this bit is 50 degrees. And so it's totally valid to measure it from the north toward the west instead of from the west toward the north. It's just then the angle changes, right? So west 40 degrees north is the same thing as north 50 degrees west. And the same deal for number 4 over here. Okay, so if we're looking at this example, what is the direction of this vector? This is example 1 over here. So we are starting measuring from the north, and we are measuring it toward the east. So we would go north 37 degrees east. And we usually put that in square brackets because you are going to be giving some sort of answer about a distance traveled or a speed being driven at or something like that. And it just shows that this is the direction part of the answer. Okay, so that's north 37 degrees east. You can also write it in any of those other ways. So it would be totally valid to write 37 degrees east of north, because you started at north and you went and you rotated east of north. So east of north or east of north, that works totally fine. The direction of the second one, we started pointing west and we rotated toward the south, right? We started west and we rotated 72 degrees toward the south. And again, you are welcome to see if you can use the other ones just as well. And finally, the direction of the following vector. We started measuring, well, you do this one. So just pause the video, or you can just end it. You started measuring south, you rotated toward the east, so it's south 41 degrees east. And that is your first set of introductory skills.